All right, so today we're talking about the disk method. So what does this actually look like? How do I do this? Let's just do an example. Okay, so I'm going to ask you to set up an integral representing a volume of revolution. All right, but I don't want you to evaluate. If you want to evaluate, more power to you. But we don't want to necessarily do that. We just want to talk about how do you set up questions like this. All right. So what do I have? I have y equals sine of x in between 0 and pi, and I want to take the area that generates, and I want to revolve it around the x-axis to create a solid. Okay, so I need a picture of kind of like what's going on. So here we go. So sine is going to look something like that. Okay, so here's pi. Here's my x-axis, my y-axis. Here's y equals sine of x, the graph of it. Okay, now I'm going to revolve that around the x-axis. So you imagine like this is just kind of like a wire frame. Okay, if I were to just imagine this wire being attached to this x-axis as like a wooden dowel, if you will, and I just spun the wooden dowel really quickly, what would it look like to my eyes? Well, it would look like some three-dimensional object. And the question I want to know is, what is the volume of that object? All right, so if I kind of like think about this thing as being revolved around that way, that's what I'm looking at. Okay, so I have this three-dimensional shape. Now, what I like to do, I don't remember the formulas to save my life. I can't remember these formulas. Okay, but I remember the method for doing this. If I imagine this thing is kind of coming out of the board, going into the board, coming out, so it's kind of like this ball, but it's like it's tapered on the edges a little bit. Then if I just take a sample from this, okay, I just take a sample out of this. Now, what is this going to look like? If I just pop this out of the board, it's going to be like a little disc. It's going to be like a little wet, like, I don't know how to describe it. I mean, it's going to look like a hockey puck in some sense, okay? So if I take this out and pull it out to the side and I just kind of tilt it, what is it going to look like? Well, it's going to look something like this. Okay, I'm going to do my best, but just bear with me. Okay, that's the little wedge. So you imagine just kind of like a book, okay, like a library. I just like slide this piece out. What does it look like? It looks like this hockey puck. Okay, so now let's look at it. Well, how wide is it? Well, it's measured along the x-axis in terms of its thickness, and so I'm going to call that delta x. So this is delta x thick. Okay. Now, what is its radius from here to here? Well, that's the radius that goes from here up to the curve. What is that height? Well, that height's given by y, which is given by, if this distance is x, then this height is y, which is equal to sine of x. Okay, so this radius here is sine of x. And so how do I find the volume of a hockey puck? Well, I take the area of this face, which is a disk, okay, that's a disk, so this is why it's the disk method, multiplied by how thick it is. All right, that's how I get the volume. So my sample volume, okay, so delta vol is just sample volume. So that's the volume of this particular section. That's going to be equal to what? The area of the face, okay, so this will be the area of the face, which is pi times radius squared, okay, so that's this thing here, times how thick it is, delta x. So now I need to go and find what the radius is. Well, radius is r equals sine of x. We already said that's the height, that's the radius of the disk. So then this will say delta volume is equal to pi, radius is sine, so sine squared of x, delta x. Now, as with any Riemann sum and anything really in kind of integration, what do? I take discrete chunks, I approximate what that chunk is, and then I take a limit of adding up all the chunks. That turns into a definite integral. Okay, so what does that really mean? If that's my sample volume, then my actual volume that I'm looking at will be take the integral of that thing over the corresponding parameter values. In this case, x goes from 0 out to pi. So this will be the integral from 0 to pi of pi times sine squared of x. Now what happens to the delta x? In the limit, that turns into the differential dx, which is how we measure distances and how we measure lengths and all that kind of stuff. Okay? So that will be the volume of this three-dimensional object, which was obtained by taking the area in the first quadrant and revolving that about the x-axis. So that is the disk method. Now I hope this method actually helps you understand like where these formulas are coming from in terms of actually deriving them kind of naturally as opposed to just memorizing what the formula is. There's nothing wrong to memorizing the formulas. For me, I just don't memorize things very well, so having this method actually helps. And I hope this picture kind of helps as like we slide this little piece out, move it off to the side, tilt it a little bit, and it shows us that it looks like a hockey puck, okay? All right, so as always, like, subscribe, comment down below, ask me further questions, post questions that you'd like me to work through, and I'm happy to keep this rolling.